So hello everyone, welcome to this lecture. So we will continue our discussion regarding how to count number of things for certain problems by formulating recurrence equations. And in today's lecture we will discuss a very interesting class of problems whose solution is a common recurrence equation, and the resultant solution for that corresponding recurrence equation gives rise to a very sequence of interesting numbers which we call as Catalan numbers. Okay, so we will also discuss various problems in this lecture whose solution is the Catalan numbers. Okay, so let me formulate this problem. So imagine the function c of n denotes the number of ways of parenthesizing the product of n plus 1 numbers to specify the multiplication order. So you are given n plus 1 numbers. Okay, I am denoting them as x0 to x of n, and I can multiply only two numbers at a time. So I want to specify the order in which I can multiply them. However, I do not want to shuffle the positions of the numbers x0 to xn. They should be in the same order. That means x0 should be there at the first position, second position, x1 should be there, third position, x2 should be there, and so on. I am not allowed to shuffle them because even though the multiplication is commutative and associative, I am not allowed to invoke those rules here. But I am interested to keep x0 to xn at their respective positions and then want to find out the number of ways in which I can parenthesize them to specify the multiplication order. So for instance, c of 3 is equal to 5 because c of 3 means I have four numbers. Okay, so I stress here if I'm considering the problem instance where there are n plus 1 number, then the resultant number of ways of parenthesizing is c of n, not c of n plus 1. Okay, so I have the number x0, x1, x2, and x3, and these are the 5 ways, okay, of parenthesizing them to specify the multiplication order. So the first ordering should be interpreted as follows. I multiply first x0 with x1, then the resultant product is multiplied with x2, and then the resultant product is multiplied with x3. As I said, I am not allowed to swap positions. That means I can't say that let me first multiply with x0 and let me first multiply x0 and x3 and then multiply it with x1 and so on. That's not allowed. Okay. In this second way of parenthesizing, the sequencing is as follows. I am first asking to multiply x1 and x2, and then the resultant product is multiplied with x0. So you see I am not changing the position of x0. And then the resultant product is multiplied with x3 and so on, right? So there are 5 ways if I had 4 numbers, and that's why c of 3 is equal to 5. So now we want to formulate a recurrence equation for c of n because I want to find out finally a closed form solution for c of n. So c of n is an infinite sequence, or it's a function which gives you the outcome for different values of n. So I want to find out the general formula or the closed form formula for this sequence or this function c of n. How do I do that? For that, I first have to formulate a recurrence equation. Okay. So let's proceed toward formulating the recurrence equation, and I am retaining here the case where I had 4 numbers and the 5 ways of parenthesizing them. So as a general principle, whenever we want to formulate a recurrence equation, we have to think of how to break a problem instance or the nth problem instance into problem instances of a smaller size, right? And then try to see the relationship. That's the general philosophy of the formulating recurrence equation. So same thing we will do here. And to break a problem instance where we are given a task of sequencing n plus 1 number into task of sequencing a sequence of a smaller numbers or less number of values, we have to do the following. I focus here on the final dot, okay, namely the last multiplication which needs to be done in any sequencing for this sequence of n plus 1 numbers. So for instance, if my n is equal to 3 here, right? Then in this sequencing, it's the final dot is appearing here. Okay, so I will be focusing on this final dot. So I can interpret this sequencing as follows. I can say that, okay, my problem instance is divided into two problem instances. Namely, I have to figure out how to sequence or how to specify the parenthesizing order for three values, namely x0, x1, x2, and another value consisting of x3. Once I know the number of ways of parenthesizing x0, x1, x2, and individually I know how to parenthesize or the number of ways of parenthesizing x3 or the remaining portion of the sequence, if I put a final dot, then that gives me a way of parenthesizing the overall sequence. In the same way, if I consider this second sequencing here, right, I'm doing the same thing. In the same way, if I consider the third sequencing, I am imagining as if I have two values here, and whatever is the number of ways of parenthesizing two values, and whatever is the way or whatever is the number of ways of parenthesizing the two values on the here, namely x2 and x3, if I put a final dot in between them, that will give me the total number of ways of parenthesizing four values, and so on, right? So the idea here is that in order to formulate the recurrence equation, I should focus on the final dot or the last multiplication. So in general, I can interpret as if the final dot is appearing between xk and xk plus 1. So remember, your n plus 1 numbers are x0, x1, x2, and x of n. So you have n plus 1 number. So you can interpret that in any parenthesizing order or any sequencing of multiplication, any parenthesizing order, if the final dot is appearing between xk and xk plus 1, then what you can say is that you have the bigger sequence consisting of n plus 1 numbers is now divided into two individual sequences, and they are disjoint. The sequence to the left hand side of the final dot and the sequence to the right hand side of the final dot. The sequence to the left hand side of the final dot has k plus 1 values. So what can be the total number of ways of parenthesizing that sequence or specifying the multiplication order for those k plus 1 values? Well, as per our problem definition, there are a total c of k ways of parenthesizing those k plus 1 values. And now we are left with remaining values, namely after the final dot. They are the values from x of k plus 1 to x of n. And again, as per the problem definition, there are c of n minus k plus k minus 1 ways of parenthesizing those remaining values, which are going to appear after the final dot. Now, if you find out the total number of ways of parenthesizing the LHS part before or the part before the final dot and the number of ways of parenthesizing the expression that is there after the final dot, then if you multiply them as per the product rule, that will give you the total number of ways of parenthesizing the numbers x0 to xn, provided the final dot appears between xk and xk plus 1. But now my k could be anything, right? K ranges from uh, 0 to n. More specifically, if my final dot is between x0 and x1, that means I am taking the case where x1, x2, x of n. So whatever way I can parenthesize x0 and whatever way I can parenthesize the remaining n values and then put the final dot, that gives me one category of parenthesizing where the final dot is between x0 and x1. Similarly, I can have another category of parenthesizing where the final dot is between x1 and x2. That means I parenthesize the subsequence x0, x1, and I parenthesize the remaining portion, namely x2, x3 up to xn. So there are c of 1 ways of parenthesizing this part. There are c of n minus 2 ways of parenthesizing this part. And if I multiply c of 1 with c of n minus 2, that gives me the total number of ways of parenthesizing where the final dot would have appeared between x1 and x2, right? And now if I continue like that, I can argue that if the final dot is between x of n minus 1 and x of n, right, then the total ways of parenthesizing will be the product of C of n minus 1 and C of 0, right? So that's why k ranges from 0 to n minus 1. Your k could be 0 or 1 or up to n minus 1. So that's why I get the recurrence equation that C of n is equal to summation of k equal to 0 to n minus 1, product of C of k and C of n minus k minus 1. Okay, and why I am adding all of them? Because all these are disjoint categories of parenthesizing, right? There is no overlap. There is nothing which gets counted twice, right? So I don't have to exclude anything, right? So this C of n function is called as the nth Catalan number. And it turns out that there are plenty of problems in combinatorics whose general solution is the nth Catalan number. Okay, so let's see another related problem. From the problem description, it might look similar to the problem of specifying the parenthesizing or multiplication order for n plus 1 values, but that's not the case. But still the answer is the nth Catalan number. So here we want to find out how many valid strings of n pairs of parentheses we can have. And what's my definition of valid strings of n pairs of parentheses? Well, if I parse that string from left hand side to right hand side, then it should be the case that each left parenthesis or opening parenthesis should have a corresponding matching closed parenthesis. That's what is my definition of a valid string of n pairs of parentheses. So for instance, this string is valid because if you scan from left hand side to right hand side, then each instance of opening parenthesis has a corresponding matching closing parenthesis. Okay, it's not the case that you have occurrence of closing parenthesis, but till that point you don't have an occurrence of a corresponding opening parenthesis. In the same way, this is a valid sequence, but this is invalid because you have an opening bracket and then a closing bracket and then followed by a closing bracket. For that, you don't have a corresponding opening bracket as of now. So that's why this is an invalid string. So we want to find out how many such valid strings of n pairs of parentheses we can have. So I have demonstrated here the total number of ways of formulating valid strings of n pairs of parentheses for different values of n. If n is equal to 0, then you don't have any string. And so that no string is denoted by an empty string. The star denotes empty string. Okay. And since empty string is one of the strings, that's why for n equal to 0, I consider that the answer is 1. Namely, there is only one way of coming up with a valid string consisting of 0 pairs of parentheses. That one way is nothing but writing down a null string. For n equal to 1, you have only one string, namely a string where you have a left parenthesis followed by a right parenthesis. Whereas a string where you have an occurrence of right parenthesis followed by a left parenthesis, this is invalid. Okay. Similarly, for n equal to 2, you have 2 strings. For n equal to 3, you have 5 strings and so on. Okay. So now we want to find or derive a formula for general value of n, right? And it turns out that the general value of n, or the number of strings for general n, is nothing but the value of the nth Catalan number. To do that, what we can show is the following. We already know that the solution for specifying the multiplication order for n plus 1 values is the nth Catalan number, because that was our starting point, right? And now we have a new problem, right? We now have a new problem, namely that problem of finding the number of valid strings with n pairs of parentheses. Instead of trying to find out a solution from scratch for the new problem, what we can show is the following. If we show that there is a bijection between the set of each valid parenthesis, each valid way or each valid mechanism of parenthesizing n plus 1 numbers and the set of valid strings that you can formulate with n pairs of parentheses, then we can say that the solutions for both the problems is the Catalan number. Okay, so how exactly we establish a bijection? So what we have to show is that you take any sequence of parenthesizing n plus 1 values. Corresponding to that, you can find out a valid string with n pairs of parentheses in an injective fashion, and vice versa. If we do that, then it establishes a bijection, right? So it might look on a very high level that the bijection establishment is very simple. What you may say is that, well, any uh, you take any sequence or any valid sequence specifying the parenthesizing of n plus 1 numbers, and if corresponding to this sequence specifying the parenthesizing order, you want to find out the matching string of matching valid string with n pairs of parentheses, what you can do the following. You can say that, okay, you remove all the terms, namely forget about x0, x1, x of n. You simply remove them, because in our valid string consisting of n pairs of parentheses, we don't have any occurrence of x0 to xn. So you can say that, okay, erase x0 to xn from your sequencing which specifies the parenthesizing order, and you just retain the parentheses, namely the left parenthesis and the right parenthesis. And the claim is that you obtain a valid string consisting of n pairs of parentheses. Well, if you do that, then resultant string will be a valid string of n pairs of parentheses. So for instance, what I'm saying is you take the sequence, say this sequence. And what I'm saying is you retain the left parenthesis, forget about A, forget about dot, then retain the left parenthesis, forget about B, forget about dot, forget about C, and then take the right parenthesis, then take the right parenthesis. So you will say that, okay, this is the valid string consisting of two pairs of left parenthesis and two pairs of left and right parentheses corresponding to the multiplication sequence where you multiply B and C first and then multiply the product with A. That's what I'm saying here basically. But it turns out that, okay, even though you get a valid string consisting of n pairs of parentheses, this is not an injective mapping, because as per this process, the sequence where B and C are multiplied first and then the product is multiplied by A will lead to this sequence, because you will forget about A, you will forget about dot, retain the left parenthesis, and then you again have a left parenthesis, then you forget about B, forget about dot, forget about C, then you have right parenthesis, right parenthesis. And you will obtain the same sequence of two pairs of left and right parentheses for another multiplication order where A and B are multiplied first and then the product is multiplied by C. So this is not going to lead you to an injective mapping. But in order to claim that the solutions for both the problems, the mapping should be a bijective mapping, and hence it has to be an injective mapping as well. So how exactly we go from this set to this set? Well, we have to convert a valid ordering of specifying the multiplication order into a string of n pairs of parentheses in a slightly different way, and this is done as follows. Okay, so you take any multiplication order specified by your parenthesizing and you erase all the terms x0 to xn, and you erase all the left parentheses as well, but you retain the dots and the right parentheses. And then, so for instance, what you do here is, if I take the same counter example for my earlier mapping, then I forget about this left parenthesis, I forget about this A, but I retain the dot, and then I forget about this left parenthesis, I forget about B, I retain the next dot, I remove C, and then retain the right parenthesis. Okay, the same I do for the other string. And now I replace each dot by the left parenthesis. If I now do this mapping, then I can show that This is an injective mapping. In fact, this is a bijective mapping from this set to this set. And that shows that the solution for the new problem is the Catalan number as well. Okay. So as I said, there are plenty of problems whose solution is the nth Catalan number. We have seen two of them. And in tutorial, we will see some other problems as well. But now the question is how exactly we find a closed form formula for the nth Catalan number. We know the recurrence equation, but that recurrence equation is not what we need. We need a closed form formula, namely a value of the nth Catalan number just as a function, as a function of n. Okay, because that will be useful if someone asks me, tell me the value of say the 100th Catalan number or the value of the 500th Catalan number and so on. So how do we do that? So for that, what we are going to do is the following. We will introduce a third problem whose solution also will be the Catalan number. Okay, and then we will derive the closed form formula for our Catalan number by solving or coming up with a number of solutions for this third problem. So what is this third problem? So in this problem, we are given 2n values, a1 to a1, a2, a of 2 of a of 2n. So we are given 2n values. And those 2n values consist of n ones and n minus ones, right? So basically it's a string of n ones and n number of minus 1. Okay, now this n ones and n minus 1 can occur in any order, but I am interested in only those sequences of n ones and n minus ones where in that sequence if I pass from left hand side to right hand side, then at every point the partial sum, namely if I am at the kth position in that sequence, then the partial sum will be the summation of the k characters which I have encountered till the kth position from the left hand side to the right hand side part, right? So basically my sequence has the values, the first value is a of 1, which could be either +1 or -1. I have the second value again, which could be +1, -1, and like that. I have the 2nth value, which could be +1 and -1. The first restriction is that in this sequence of 2n values, +1 should be there at n positions, -1 should be there at 1 position. That's one of the restrictions. And the second restriction is that if I go from LHS to RHS, that means from the starting position to the end position, and if I stop at any position, k. It could be the first position. If I could stop at the second position, I could stop at the third position. If I stop at any position k, where k ranges from 1 to 2 of n, and if I take the summation of the first k values which I have encountered till now while scanning, then that partial sum, I call it as S of k, and that partial sum Sk should be non-negative. That means it should be greater than equal to 0. It could be 0 or it should be more than 0. So in some sense, intuitively what it means is that if I pass from left hand side to right hand side, then at each and every position, the number of occurrences of +1 should be either more than the number of occurrences of -1 or it should be same. It should not happen that the number of occurrences of -1 is more than the number of occurrences of +1 at any point of time when I pass the sequence from LHS to RHS. So for instance, this automatically means that my string cannot start with -1. Any sequence, any valid sequence satisfying these conditions cannot start with -1. Why so? Because if I take k equal to 1, then my partial sum S of 1 becomes -1, and that automatically shows that this is an invalid sequence. So it automatically means that my sequence has to start with +1. So I can have a sequence where I have all the +1s appearing first and then all the -1 appearing later. That's a valid sequence. Or I can have a sequence where 1 and -1 occurs alternatively. Okay, that's also a valid sequence, and so on. But I can't have a sequence of the form where I say start with 1 and then I have a -1 and then I have a -1. No, that's not allowed, because if I take this partial sum S3 in this sequence, then S3 becomes -1. So that's not allowed. So I am interested to find out the number of sequences consisting of n1s and n-1s satisfying this condition. And it turns out that the number of sequences satisfying this condition is exactly the same as the number of valid strings consisting of n opening parentheses and n closing parentheses. This is because you can interpret the following. You can interpret the new problem as the following, right? You take any valid string consisting of n opening parentheses and n closing parentheses, and you replace the opening parentheses by 1, and you replace the closing parentheses in those valid strings in the valid string by -1. So you will obtain now a sequence consisting of n numbers of +1 and n numbers of -1, and you will see that in that string of n number of 1 and n number of -1, the number of ones is always greater than equal to the number of occurrences of -1 at any point of time if you scan that string from left hand side to right hand side. So for instance, if you take this string, that this gets converted into 1 followed by -1. Okay, if you take this n equal to 2 case, then the corresponding string is, you have 1, then you have a closing parenthesis, so you put -1, then you have an opening parenthesis, then you have a closing parenthesis. Okay, whereas the second string gets mapped to the following. You have left parenthesis, so you have 1, and then you have 2 closing parentheses, so -1, -1, and so on. Okay, so that shows that the solution, or the number of valid sequences satisfying our condition, is same as the number of valid strings with n pairs of parentheses. And what we will show in our next lecture is that the number of valid sequences satisfying these restrictions is nothing but this formula. So this C is not the Catalan function. This is now the combinatoric function, or this is 2n choose n. Okay, and it's basically the number of ways of selecting n values out of 2n values. So the nth Catalan number, its value is 2n choose n over n plus 1. Okay, this we will prove in our next lecture, right? So that brings me to the end of this lecture. These are the references for today's lecture. So just to summarize, in this lecture we introduced Catalan numbers. We saw 3 problems, and the solution for each of those 3 problems is the recurrence relation for the recurrence relation for the Catalan number. And we also I have shown you the value of the nth Catalan number. In the next lecture, I will explicitly solve the recurrence relation for the recurrence relation for the Catalan number, and we will derive that the value of the nth Catalan number is 2n choose n over n plus 1. Thank you.